Hello, and thank you for tuning in to this discussion of joint optimal order quantities in a supply chain. Previously, we talked about the basic EOQ model, and what we really did was we chose order quantities so as to minimize the inventory holding and order placement costs for a single company, such as, for example, a retailer. We should realize that we're talking typically about supply chains, so whatever a buyer such as a retailer orders ultimately comes from a supplier, which could be a manufacturer, for example. So buyer's choice of an order quantity will also affect a supplier in terms of the supplier's inventory needs. Think about it. Assume that a supplier has a production quantity of 1,000 units. So that means that the supplier produces 1,000 units at once. But now, if as a buyer you only order 100 units at a time, the supplier will be left with extra inventory. The question is this optimal for the supply chain? This is what we want to discuss in this video. We want to calculate order quantities that are aligned throughout the entire supply chain, meaning we want to align the supplier's order or production quantity with the buyer's order quantity. The notion being that if we do that, we're able to minimize total system inventory and associated costs. Our objective is to align these production and order quantities to basically constrain them to be equivalent, and we will see in a moment that this will yield minimal cost, not just for the buyer or supplier respectively or individually, but actually for the entire system. So let me walk you through an example here. I've set up a little table with some data for the buyer, as well as data for the supplier. So looking at the buyer first, we are looking at a total annual demand volume of 10,000 units, an order cost of $50, a unit cost of $15, and a holding cost factor of 12%. When we compute the basic standard EOQ, we would get an order quantity of 745 units. Again, this is simply the square root of 2 times annual demand times the order cost divided by the inventory holding cost per unit per year. Now we can do this same thing for the supplier. Again, similar data. Note that here the annual demand volume is the same as for the buyer. So we assume that this supplier only produces one product for one buyer. So we're talking about the same 10,000 units here. Production setup costs, similar to order costs, amount to $200. Unit costs are $10. Of course, they are lower than for the buyer, because the buyer will have to pay some profit margin to the supplier. We're talking again about a holding cost factor of 12%, and if we are able to compute the supplier's economic production quantity in the simplest way, so basically using the same formula as the EOQ, the square root of 2 times lambda times k divided by h, we would then find that the economic production quantity would be 1,826 units. So this, where we see the problem, you see that the buyer would rather order less than the supplier produces. But if that were to happen, then we would clearly end up with extra inventory sitting around at the supplier's site until the buyer decides to order again. This is what we want to avoid, and I will show you that it is in fact cost minimal to align these two quantities. So now let's take a look at this table I have set up here. We're basically looking at 3 different scenarios. If we want to constrain these orders and production quantities be equal, we can either assume that the buyer is able to impose her optimal order quantity onto the supplier, in which case, of course, the buyer would choose an order quantity of 745. Similarly, we can assume that the supplier is in control, so the supplier can force the buyer to order the supplier's optimal production quantity at a time. So we would be looking at 1,826 units. And then thirdly, and this of course will be of the greatest interest here, we could find a jointly optimal order quantity that truly minimizes the entire supply chain cost, meaning the sum of the buyer's and supplier's costs. So what I would like to do first is I would like to compute the buyer's and supplier's cost for each of these solutions. Let's look at the buyer first. If the buyer can impose her EOQ, the buyer will minimize her own private or individual costs. And of course, these costs are simply the sum of inventory holding cost and order placement costs. Inventory holding costs will then be average inventory, which is Q divided by 2 multiplied with the relevant unit cost of $15 and the holding cost factor of 12%, plus the order placement costs, which will be annual demand divided by the order quantity multiplied with the cost of placing an order. So we'd be looking at a total cost for the buyer of $1,341 roughly. And then for the supplier, it will be very similar. For the supplier again, we compute the sum of inventory holding and ordering costs. So inventory holding costs would again be average inventory And again, we would constrain the production quantity to be equal to the buyer's order quantity of 745. So average inventory would be half of that multiplied with the relevant unit cost of $10 and the inventory and carrying cost factor of 12%. Add to that the annual production setup costs, meaning annual demand divided by this production quantity multiplied with the cost of a production setup. So that would give us roughly $3,130 for supplier's cost. So the sum of those two would represent the total supply chain cost, which in this case would be approximately $4,472. Now we can of course do the same thing assuming that the supplier is able to choose that joint order quantity. All I will do now is I will simply drag these formulas over to the supplier, and you can of course type these formulas separately if you like, but you will clearly obtain the same results. So not surprisingly, you will see that if the supplier is able to impose her individually optimal production quantity, the buyer's cost will be higher because the buyer is deviating from her individually optimal order quantity. And conversely, the supplier will be able to minimize her total relevant costs. You see also that from a supply chain perspective, clearly it will be preferable for a supplier to set the joint quantity rather than for the buyer to do that, at least in this case. Now our question then of course becomes, well, is there some other quantity that may actually minimize total costs even further? Well, you'll see that the buyer's Q is 745, the supplier's Q is 1,826. So let's assume that the jointly truly optimal order quantity is somewhere in between, let's say about 1,000 units for the time being. So let's compute again the total cost for buyers, suppliers, and total supply chain costs if we assume an order quantity of 1,000. And you can see already, even though I arbitrarily picked 1,000, I was able to further reduce total supply chain costs by 4,000 by choosing this 1,000 unit joint order quantity. Now this is not optimal yet, of course, because I arbitrarily selected 1,000. So what I'll do is I'll use Solver to find this truly cost minimizing order quantity. So what I want to do is I want to minimize the total supply chain costs by changing the value of this jointly optimal order quantity. I'll just click on Solve, and you see that the truly cost minimizing supply chain cost minimizing order quantity will be 1,229 units for a total supply chain cost of $3,873 roughly. Now one more thing that we need to talk about real briefly is how do we actually make these kind of solutions happen. So let's assume, for example, that the buyer is actually in control. We're talking about a very powerful retailer that purchases from the supplier. Well, how could the supplier actually motivate the buyer to deviate from her individually optimal solution? Because you can see that by choosing this quantity, the buyer's cost will be higher. Specifically, this cost difference would be equal to approximately $207. So clearly, on the other hand, if we look at the supplier side through the supplier, would actually save a lot of money by not having to take the buyer's order quantity as her production quantity, but rather having a jointly optimal order quantity. So what would happen, in effect, is that the supplier would have to pay or reimburse the buyer for her extra costs, and maybe also add some extra incentive in terms of sharing the additional savings. But clearly you can see that with these kinds of savings to the supplier of $807, the supplier can easily reimburse the buyer for her extra costs and still make about $600 in savings relative to the initial scenario where the buyer imposed her order quantity onto the supplier. Now conversely, of course, we could do the same thing assuming that the supplier is in control, which would mean that the buyer would have to reimburse the supplier for any extra costs that the supplier incurs from deviating from her individual optimal production quantity. This is important to consider when we talk about the implementation of these kinds of jointly optimal schemes in supply chain. If you have any questions, as always, I invite you to ask me at any time.